So friction is of two kinds, solid friction and fluid friction. Solid friction is friction between two solid surfaces, and fluid friction is between two fluid layers. Fluids such as gases and liquids, they move in layers. Although we may not be able to see those layers, they are molecular layers. So if you have water going through a pipeline, water actually is moving in layers like that. You can check it out experimentally by doing the following. If water is moving through a pipeline, if you can insert a dye or something like that, a little bit of dye at a certain place. If you release a little dye here, you will see the dye. Dye is something that mixes with, not you. Dye is something that mixes with water. But then when you release the dye, it actually kind of goes like this in a straight line. For quite a distance, it goes in a straight line, then it just diffuses. So why is it going in a straight line? It's because of the existence of those layers. Okay? So those are experimentally proven. So fluids are moving in layers. So a fluid layer, by itself, fluid layer, you can understand what it is. So if you take a pipeline like this again, there are many fluid layers. There's a layer of fluid stuck to the inside edge there. It's a cylindrical thing. So, and there's a fluid layer stuck to the surface here. So there's a fluid layer stuck there and here, right? The next fluid layer is free to move. Even though it's free to move, between the stationary layer and itself, there will be a little bit of friction. So therefore, the second layer is not going to be able to freely move at its own speed. It is restricted. What about the third layer? So the second layer is restricted. Third layer is less restricted. So it's able to go faster. Fourth layer is going faster, 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 faster. And then when you come to this side again, the story repeats. So you can see the liquid actually kind of goes in that shape. The front of the liquid will be in that shape. Why? Because the center of the fluid, the layers in the center are least affected by the stationary layers. Make sense? The central layer is least affected by the stationary layer. So these will go fastest, and there's a drag. That's what we call as a drag force, fluid drag, the air resistance, the air drag, all those things. Drag, the word drag is basically this. The faster moving layer is dragged by the slower moving layers. That is basically a kind of friction. Even in a classroom, the faster learning student is dragged a little bit by the slower learners, right? Yes, true. Because the slower learners will actually keep asking questions, which the fast learners already have understood. So the teacher will actually slow down and stop and explain this. Not a mistake, but that will actually make the fast learners kind of bored for some time. Now imagine they're all fast layers, fast students. Then it goes like that. Because everyone is like on the same boat. There's nobody asking questions like, so what exactly is Newton's second law? Well, in that case, I just have to go back all the way and explain Newton's second law, when all the others will say, no, come on, Newton's second law, everyone knows. I hope it. I hope everyone knows, okay? All right, anyway, that is what we call as a drag. Compare this with another example. Imagine there is a one-way road made up of 5 lanes. The last lanes are places where people park their cars, okay? Then you have 3 lanes to go. The central lane will be least affected by those parked cars, right? But what about the lane next to those parked cars? Can they move very freely? They can't move freely because there are parked cars next to them. So God knows what's going to happen. Like, is there a child coming out from between the cars, or someone opening the door from that side? We don't know. Therefore, the one who's going next to those parked cars will be vigilant, right? And therefore, he can't go at 45 miles per hour next to parked cars. Whereas in the middle layer is more free. They can go, right? That's because of the drag. So we are talking about fluid drag, which is that. Now, coming to solid friction again. Solid friction is two types. We learned it. We have static friction and we have kinetic friction. Now, static friction is a friction between surfaces when they are not moving. So static friction can take different numbers. Can static friction be 0? Yes, no?
No.
What's the static friction on the book right now? 0. Then why did you say no? The static friction on the book is 0. Why? Because nobody's attempting to apply a force on it, and therefore there's no need to apply an opposition. You understand what I'm saying? So the book, right now, the static friction is 0. The Fs can change from 0 up to a limit. So that's why I gave you the graph. The friction can grow evenly up to a limit, which is called static friction, limiting value. So when we say static friction, we are talking about the limits, the maximum. How much is the maximum static friction that is actually applied, that can come into existence? We are more concerned about that, not the zeros, not the 1 Newton, 2 Newtons and all that. So these are all there, but what is important to us is that the moment it is about to slip, that's called the limiting value of static friction. We can write it down. Limiting value of static friction. So when you say Fs, we imply that it is a limiting value. As soon as it starts slipping, then the kinetic friction, Fk, comes into play. And you know the Fk is smaller than the static friction. Fk is just one value. It's not growing from 0. Fk is a steady number. Static friction, yeah, Fk is kinetic friction, or this is kinetic friction. The kinetic friction is a single number. Whereas static friction can take numbers from 0 to a max. Is that clear? Kinetic friction is just one value. And the static friction can build up to a maximum value of limiting friction, that is, so the Fs, I'm taking this graph off. Okay. So the static friction keeps growing. As we know, what are the factors the static friction depends on? Fs is proportional to what? Did we say some of the things? Yeah. Static friction will involve applied forces and all that, but applied force is what is causing the static friction. But we are trying to find out what is static friction dependent on. Okay, so if you don't apply a force, there's no static friction. That's true. But then we are talking not about any other static friction. We are talking about the maximum, the peak. The moment the objects are going to slip, that friction, like when I push this book, when did it just slip? When I cross that limit, right? That limit is what we are talking about. So therefore, we don't apply, we don't worry about applied forces. So what is that limit controlled by?
The normal force of the surface.
The normal force applied by the surface on the object. The normal reaction. Static friction, the limiting value of static friction depends on the normal force, the force applied by the surface on the object. If you're talking about your car, then how much force is a car applying on the surface? That much force the surface is applying on you, on the car, that is a normal reaction. So static friction depends on that. And what else static friction depends on is the nature of surfaces. Nature of surfaces. What is the surface like? Is it glass with glass, glass with rubber, rubber with rubber, concrete with rubber? What kind of surface are we talking about? The book with a table, or book with book? So that is the nature of surfaces. So depending on the nature of surface, it's going to be different. And so F is proportional to NR, and F is equal to a constant of proportionality times NR. You know the constant of proportionality concept, right? If you have a proportional sign, and then if you want to convert it into an equation, we need to bring in a constant, right? And this is what we call as the coefficient of static friction. Coefficient of static friction. Coefficient of static friction is this mu s. And what is this? It is the static friction, the limiting value, the peak value. When it is about to slip, when things are about to slip, that is equal to mu s times nr. Mu s is a coefficient of static friction. It has no units. It has no units. It's purely mostly a number, a decimal value, a fraction. For instance, I'm just giving an example now. When I tried to move this book, when I tried to move the book on the table, let's say the book was 5 kilograms. What is the normal reaction? So before you decide what is normal reaction, find out how much the book is applying on the surface. How much? 9.8 times 5, because 5 kilogram means this book has a weight of 49 newtons. The book has a weight of 49 newtons. The mass of the book is 5 kilograms, the weight of the book is 49 newtons. So when the book has 49 newtons and is sitting on the table is not letting it fall under gravity. That means what is the table applying on the book? 49 newtons. So the normal reaction is 49 newtons. We have seen this before, many examples. So the book wants to go down because of gravity, but the surface is refusing it. How much is the normal reaction? Trying to cancel off that force of gravity, it's 49 newtons. So we know the normal reaction is 49 newtons. All right? Now if I don't apply any force, how much is the frictional force? 0. If I apply 1 newton, it is 1 newton. I apply 2 newtons, it is 2 newtons, it's growing. And let's say it has a limiting value. Suppose the limiting value is this. The moment I applied 15 newtons, it slipped. What does it imply? As soon as I applied 15 newtons, the whole thing slipped off. So what did you understand about the maximum Fs that it could hold on to? How much? 15. The graph is going up. Maximum friction that it could hold on to is how much? 15. And that is, so at 15 it slipped, implies that the static friction just built up to 15 and after that gave up. So how much is the static friction? 15. So Fs is equal to mu s times normal reaction, substitute. 15 is equal to mu s times 49. So what is mu s? 15 over 49, which in decimals is 0.3, 0.31. What is 0.31? It is the coefficient of static friction between the book and the table. Make sense? That's the coefficient of static friction between the book and the table. And between the book surface and the table surface, that is a number, whatever be the object. Like if I keep 2 books, doesn't matter, still the same thing applies. If I keep 2 books on each other, how much force can it hold on to? If I keep 2 books, similar books on each other, how much force will this hold on to? What's the limiting value? If I keep 2 similar books, one on top of each other, how much will Fs build up to?
30?
30. Yeah. Static friction, it depends on normal reaction. When you put 2 books on each other, what's the normal reaction? it is now 98. So if it is 98, then this will build up accordingly because a number, this number 0.31 is a fixed number between the book surface and the table surface. It's a fixed number. Yeah.
Just wanted to clarify, so that's just like the proportion between
Static friction
static friction
and normal reaction.
Okay.
So basically, coefficient of static friction is a ratio of the limiting value of friction to the normal reaction. Yeah,
Is it always that way, or is it different depending on what surface you
doesn't matter. It's always like that. The only thing is, if I'm going to use this book on glass, I may not be requiring 15 newtons to get it slipped, right? So probably then the coefficient of static friction between the book and the glass is like lower, 0.2, something like that. Now, if I'm going to keep this book on ice and then slide it, it'll be requiring the least force to get it started, right? So maybe 1 or 2 newtons will be enough to make it go. So it'll be like 2 newtons divided by 49. So that will be the coefficient of static friction between this surface of the book and the ice. Now if you're talking about one ice block on another ice block, then you can, before it actually like sticks onto each other, if it's going to slide, it's going to be definitely much smaller. So a metal object on ice is definitely going to cause very little friction, especially if it's wet ice. If it's wet ice, a metal object will slide with almost negligible amount of frictional force. Do you get it? And yeah, ice skating, the blade which rests on the ice applies a pressure enough to melt the ice at that point, because the pressure changes the melting point. So when you apply a pressure on a particular point on ice, it melts that point. And that's why slipping becomes easier. Make sense? All right, so coefficient of static friction, is this part of it clear? When you are applying these into problems, then you have to take all these points into consideration when you actually look into a problem. That's why I'm slow on this. Make sure you understand this. So Fs is equal to mu s times normal reaction. It's an important force, important equation. Keep that in mind. Now, coming to kinetic friction. Kinetic friction also depends on normal reaction and it depends also on the nature of surfaces. So we have mu k times nr. The coefficient of kinetic friction between the book and the table will be smaller than mu s. So in our example for static friction, how much was the force needed to get it going? How much was the friction? 15 newtons. But after it starts slipping, if I want to maintain a constant velocity, I need to just apply 10 newtons. See? I need to apply only 10 newtons and it keeps going. That means what is the kinetic friction? It will be 10 newtons. So once the book starts sliding at constant velocity, then you're applying a force this way, but the kinetic frictional force should be equal to what you're applying, right? So if I'm applying only 10 newtons to keep it going at constant velocity, Fk will be 10. I'm just throwing numbers. It doesn't have to be exactly these numbers, yeah.
So it doesn't matter if you're moving at like 80 miles per hour or like 60 miles per hour.
It doesn't matter.
If you apply the same force, it's going to keep
It
going.
is, yeah. I can move it at a constant velocity of 10 meters per second or 2 meters per second. Once it is moving, it is fixed. That's why the line was horizontal. Do you see that line on the graph? Once it starts moving, immediately it becomes a steady line. How fast you go doesn't matter. All right, so constant velocity. So what's happening here now is Fk is 10. How did you decide Fk was 10? Because I told you I'm applying 10 newtons and it is moving at a constant velocity. So obviously, this must be 10. If this was less than 10, it should have. If this was less than 10 when I applied 10, this should have.
No.
Accelerate.
Accelerated, because 10 and 8 or something like that, it will be accelerating. You understand? If I'm applying 10 and if this is like 12 or something, it will decelerate. From this velocity, it will slow down until it comes to halt. So when it is moving at a constant velocity, it is definitely equal. Okay? So those are some clues that you have to pick up from problems. Because they'll tell you an object is sliding at a constant velocity. Boom, over. You got the clue. It's moving at a constant velocity. That means whatever is there making it go at a constant velocity is the kinetic friction value. Make sense? I repeat this again. In the problems, they won't tell you clearly what is what. They won't tell you kinetic friction. Instead, they will word it like this. The object is moving at such and such a velocity when this much force is applied. And then they'll ask you further questions. They won't tell you whether there is a kinetic friction existing or not. You should understand it. When they say something is applied and yet it is moving at a constant velocity, what does it mean? It means there is definitely something opposing it, and that opposing force must be the same as the applied force. So that conclusion that you come to during problem solving is a very important thing. All right? It's just not F is equal to ma. The whole chapter is based on F is equal to ma ultimately. But how you apply it is important. How you pick up clues is important. So Fk is proportional to normal reaction, and Fk also depends on the nature of surfaces. Fk does not depend on how fast you are moving. You can write it down. Fk does not depend on how fast you're moving. Alright, you learned enough here. Now let's go to fluid friction and look at some of the concepts of fluid friction. So what is fluid friction? Fluid friction is one fluid layer applying a drag force on the other fluid layer, right? It could be actually fluid with fluid, or it could be a fluid layer stuck with an object rubbing against another fluid layer stagnant. Like if you throw a baseball, there's a layer of fluid or air stuck on the baseball, and the baseball is moving against a standing layer of air. So there is a little rubbing there between the two layers, and that is what we call as the air resistance or the drag forces. Now those fluid friction depends on what factors. So what is fluid friction? Again, it is the friction between one fluid layer against the other fluid layer. Let's say your car, there's a fluid layer stuck with your car, and there is stagnant fluid layer on the road. So when you're actually moving, those two fluid layers are rubbing against each other. Factors. What factors? Huh?
Surfaces.
Nature of fluid?
Sure. Yes.
Okay. Nature of fluid. Because when you say surfaces, automatically it means that what kind of surfaces, and therefore nature of fluids. Yeah. Is it air or is it water? Look at, yeah.
If you were driving your car and it just rained and you had you had water on the wheels, would that still be static or would that be like fluid or would it be?
There are lots of frictions on the car. Are you talking about the drag forces? Or are you talking about the friction between the tires and the road? Those are different things.
Okay, so
The grip that you get between the tires and the road, that is slightly less compared to when it is dry. So when it's dry, you have more confidence in hope in stopping the car at the right place, right? But when it's wet, there is a fluid between your tire and the road. There's a fluid layer. And if the fluid layer becomes a little thick, then it becomes very slippery, and that's called hydroplaning. Your car won't be in your control, because if you're actually going through sufficient amount of water, that fluid layer between your tires, under your tires, and the fluid layer over the road, those two are now going to cause fluid friction. Normally fluid friction is much smaller than solid friction, much smaller. So when there is fluid with fluid, it is definitely going to be more slippery. Like for example, right now this floor and my shoes is very good grip. I can actually run around to some extent, but Imagine it is wet over here and my shoes are also wet. It's going to be difficult, right? Because now we are talking about fluid friction between the surfaces. So if it's oil with oil, done. Like imagine your shoes are soaked in oil and the floor is oily. It'll be very slippery. So nature of fluid, very important factor. And then what else? What else does it depend on? Like definitely it is dependent on this. There is no normal force, unfortunately, in this one. Right? Normal force means force offered by a surface on an object perpendicular to surface. No, that doesn't actually apply here. Normal force does not exist. Yeah.
Would it be the distance between the solid surface?
Which solid surface?
Well,
Oh, you're talking about the hydroplaning thing?
yeah. So, well, like the water pipe, so like the fluid friction of like the water on the stationary pipe is greater than it
Yeah,
when
yeah.
it's like farther.
That is why I said if there's a very faint layer of water on the surface of the road and your tire is like just wet a little bit, it is not going to matter much. Why? Because the two surfaces are very close. So they'll offer sufficient amount of friction. But when you have a puddle of water, now you're talking about layers that are far away. And that's when it becomes more slippery. Make sense? That's when hydroplaning takes place. Hydroplaning won't take place on normal roads like that. Especially if there is a little extra puddle, that's when you have this problem. Hydroplaning. Which is pretty dangerous because during the hydroplaning moment, even if you try to, and if it takes place at a turn, if the hydroplane takes place at a turn, you have no control of the steering wheel because whichever way the steering wheel is, it's going to go straight. And that's going to be troublesome because then you lose control and it goes to the next lane. Yeah.
What's the best way to stop hydroplaning? Like, I don't know if like
Read your driver's manual.
I don't know. I've been in some of the hydroplaning things. First thing is reduce your acceleration. Cut off the acceleration because your attempt to spin it, that is what makes it worse. So cut off. And don't apply brakes. Try to let it establish because if you apply brakes, you are not depending on static friction between the tires and the road. You're trying to make it kinetic. Because if you lock the brakes, it's kinetic friction. And you know kinetic friction is smaller than static friction. So if your wheel is like locked, then it starts gliding and the force of friction is going to be much smaller. So let it let it keep rolling. You have to let it roll because when it's rolling, it is static friction. Watch. When it's rolling, it is static friction because the tire is in contact with the road and it makes new contacts. Make sense? So once you lock the wheel, then it goes like this. That is kinetic friction. So the one thing you should do immediately is cut off the acceleration. Don't press the brakes. Instead, try to focus on how you can acquire the grip again and then try to move around whatever object. Well, you can do whatever you want, but if the fate is on against you, you will actually end up hitting someone. There is no chance. But you can avoid it by not accelerating it, because if you try to accelerate and try to move around, that's bad. And at the same time, if you try to apply brakes very sternly so that you will stop, you will never stop. You'll go and hit for sure. So let it kind of grip and roll, and you can pump your brakes a little bit. Touch. Don't let it catch up. Just let it pump. They use the word pumping, like touch, release, because when you touch it and release it, the engine is actually taking over the effort to get it back into the right speed. So therefore, you'll see that the engine will slow you down much better than instead of locking the wheels. A lot of things can be done, but it all depends on your presence of mind at that moment. And sometimes when you see the danger right in front of you, you will not be able to think about pumping and all those things. And you will try to apply the brakes very stiffly, and then accident is for sure. So if you're dangerously driving close to another car, that is a bad thing. especially on a rainy day. If you're trying to dangerously drive back to back, you're inviting trouble. Keep a sufficient amount of gap. Leave from home early so you don't have to race. Leave from home early. There's no rush. And let people get in front of you, no problems. But you just keep that gap enough. You understand what I'm saying? So the stopping distance, we'll see later on in different chapters that we talk about stopping distance. So the stopping distance must be larger than usual days. So in case somebody hits another car and he's already come to a halt and you're behind, you are going to stop hitting that car. Impossible on a rainy day. You will hit it hard and you'll go and ram into the others. That's why on an icy surface, can you drive a car? Yes, but keep a good distance, drive slowly, and you should be able to drive even on an icy road.
Thanks, Mr. Sam.
What?
Thanks.
So if you try to drive as if it's a normal day, close by each other, and then at the speed limit, a speed limit says 35. I'm going at 35. Rubbish. You go at 10 or even 5. That'll be the best thing for you. Okay. Yeah.
Is sliding on ice the same thing as motor pointing? Just
No, ice. The coefficient of kinetic friction on ice is very, very small. So it's like almost like ice skating, and that's especially with your big 2,000 kilogram car. You know, there are only 4 tiny contact points between your car and the road, and you are thinking that you're controlling the car. You are a driver. You are the driver of this 2,000 kilogram monster, and there are only tiny contact points on the road, and the steering wheel in your hands. And so think of this. Your responsibility is far more than what you think. It's far more than what you think. It is a big thing that you're moving around, and therefore if you have to establish control of the car on the road, you need to be very responsible. Keep good distance. Don't try to, and even if someone overtakes you and then, blinks the lights at you and then, scolds at you or points at you and all those things, don't lose your temper. Somebody's mad, don't lose your temper, because once you lose your temper sometimes, what did he say? Okay, let me see who that guy is. You try, and then you'll be in an accident, for sure. Let him go. There are so many mad people on the road. There are so many people on kind of rage. They are not happy people. And therefore they may do something that may initiate something in you. And you, being that young blood, you say, no, I don't want to accept this. Let me go and stay in your car. So you just drive cool. Let them do anything they want. You, your car, your lane, that's it. No other thing at all. If you take care of yourself this way, no problems. And you have to anticipate mistakes can happen. You've got to be anticipating mistakes can happen. You can't just think that everybody is going to drive right. Don't think that. People can suddenly move lane to lane right in front of you or even beside you. Like 2 cars like this. You're in the blind zone. They will just come into you. And therefore that can put you in trouble. So definitely never drive parallel to somebody. Especially an old person. Or, I don't know. Okay. Okay, an old person or somebody else, don't drive parallel to each other because they will not be able to see you. First of all, their eyesight's bad. Secondly, a lot of other factors. So they just, move in and they won't see what consequences coming through. So therefore, dangerous. Anticipation of what can go wrong in front of you should be a very important thing. So if you see a boy standing on the roadside, he's on the side. Don't think that he will be disciplined enough to stand there until you cross. Thinking like that and going at your regular speed is your mistake. Don't expect him to be staying there. He's not very responsible. All of a sudden, he'll jump in. One boy almost got under my wheels on Westport Road. I saw him on a bicycle, little bicycle. He was a small boy. He's on a bicycle. He's standing like this, ready to, get onto the road. Probably he wants to cross or something. I saw him from a distance and I said, that doesn't look right. He's kind of standing ready to kind of move in. Will he move in or not? I was suspicious about it, but I was ready. I was really ready. And as I anticipated, he just suddenly came inside. I hit my brakes and the distance between him and my car was like that much. I was just saying like, okay. Now, would I have stopped him? I mean, would I have stopped the car if I was like not really concerned about it? Because he was on the curbs, like the road is that. He was on this side. What makes him come down here? Probably he was standing, that's my guess. He was standing right on the edge. The front wheel was right on the edge of that thing, right? And then all of a sudden it rolled forward and he had no control of holding it back. So he just went in. There are lots of idiots like that. So don't anticipate that things are going to go always right. Always think that, okay, that guy is maybe he's trying to change lanes. I have to be careful. Or he's trying to open the door. Be careful. Keep warning yourself and you'll see how good a driver you are. Yes?
So like, I was taking my driver's test, it was like, the question was like, when does the road like most slippery, like slippery conditions? It was like rain after a long dry spell. Why
Yeah.
would that be like?
Rain after long dry, because of the slush on the road. There's dust on the road.
Yeah.
And when it just rains, the dust is kind of pulled out, and that makes it a very slippery surface. Now, once it rains for a long time, your car will be much steadier, other than the hydroplaning thing. But if it was completely dry for many days, and then a fresh rain comes in, and the road is just wet, and that's very dangerous time.
Have you ever had any issues with like slippery roads?
Only once when I was coming from downtown on 64. Now they changed the roads and all that. Previously the road was actually kind of coming down like this and dipping a little bit, and there was always some water clogged over there. Previously, now they changed everything. So yeah, especially that water of this much layer of water for a certain distance was there. And most of the time it's okay, but sometimes, especially if this will happen, especially if you have old tires with less tread on it. Listening up, hydroplaning will not happen for new cars, because the new cars will have sufficient gap to kind of expel the water, right? So if this much water is there on the road, won't be a botheration for new tires. New tires, not new cars, new tires. And if the tires are almost like flat, then what will happen is the water has nowhere to go, so it gets locked. You understand? It just gets locked. It's almost like, I'll show you. I'll show you this. Look at this. This is absolutely, think of this as a tire. Think of this as a tire, and I'm just throwing it on this table. Watch what's happening here. You can see that a little bit of slipperiness is there. Let me try this way. Look at that. I dropped it here. It went so easily from here to there. Why is it happening? Because there is air trapped in between. That's why. Now imagine that to be a tire and a road, and there will be water caught in between, and it has nowhere to go, and that's when you have hydroplaning issues. Now suppose I make a lot of holes over here, and then I do this. Will it slide? No, because the air will escape from those holes. And that is where the new tires will have those treads, so the water will be like squeezed out from them. Make sense? Yeah. So a lot of things on the road, in your car, everything, there's a lot of physics there. And you have to understand those physics gradually. People who are driving blindly and all that, without knowledge of physics, of course, knowledge of physics will actually give you a reminder at every moment. When next time when you see, as he pointed out, next time when you see a fresh rain, you will be thinking about him. And our discussion.
Fresh rain, I think
Yeah, so it is important that, and the next time you're going ice skating, you'll be probably thinking about me, because I told you that pressure makes the ice melt, and that makes it slippery, more slippery than any. Ice and ice by itself is not really that slippery, but the water between the ice is what makes it more slippery. Ice and ice kind of grips very well, but the water makes it slippery. All right. We are still on this. Nature of fluid. And what's the next factor? Let me give you an example. Let me give you an example. Pay attention. Imagine there are two people walking in knee-deep water. There's water and two people walking in knee-deep water. One has fat legs. One has fat legs and one has blade-like legs.
Oh, that's me.
Okay? Now, who will find it difficult to walk through that water? The fatter one or the fatter one, obviously. So, what is different between them? Surface area. So, fluid friction depends on surface area, whereas solid friction was independent of surface area. I discussed that earlier. Solid friction was independent of surface area, right? But here, fluid friction depends on surface area. So, how much surface area does your car have? The drag forces will be dependent on that. Okay. Now think of the same two people. So the one with blade-like legs can cut through the water, but this will have more air resistance. Okay. The other fact again, the fat one and the skinny one. Imagine they're both attempting to walk faster or run. They're both running under knee-deep water. They're both walking or running in knee-deep water. Who will have more fluid resistance? The fat one again. Right? Or think of this. I think it's better not to give that example. Think of two people with identical kind of legs. Two people with identical surface areas. If one is walking and the other is running, who has more drag forces? The running one. And that's why if you try to run knee-deep water, you will trip and fall because the top part of the body says go, but the bottom part is being pulled backward. So you end up falling. And if you want to really run in water, what you should do? Lift your legs up. Exactly, because air resistance is negligible compared to the fluid resistance. So you some kind of leap. You have to jump out and then make your step. And that way you can actually be faster if you're running in water. If you try to go like that underwater, that's going to be tough. All right? So, depends on what?
I miss that one.
Depends on relative velocity. It depends on the nature of the fluid. It depends on the surface area. And it depends on the relative velocity. So, you can put all these things together. We are not looking at it into an equation format now because that is beyond the scope. To find out exactly what is the frictional force for an object, we need a constant of proportionality, which is called coefficient of viscosity. But we are not going that far. So right now, understand the factors only. Here, depends on the nature of surface and normal reaction. It does not depend on area, it does not depend on relative velocity. Got it? Whereas over here, it does not depend on normal reaction, but it depends on area and relative velocity, which this one was independent of. So, fluid friction. So, like a truck and the driver's compartment. This is basically what it is, but they have something here like that, a dome. Why they have that dome over there is to reduce the surface area, because what if air is coming and blocking it like that and climbing over? So that's kind of more of a resistance. So this way it streamlines the air better to make it go. That's why your windshield is like that, tilted, not flat. If you have a car with a windshield like that, as it used to be in the past. Why those cars are not going to be good these days is because we have better speeds. And those cars were going only at 10 miles per hour, then it's okay. If you're going at 10 miles per hour, this is not going to be a major issue. But for cars that are going faster, now we have windshields that are going like that. Right? It's like tilted. So the air kind of glides over. So air resistance will be lesser in such cars where you have. So the aerodynamics of your car and all that is a very important factor. So that is fluid friction. Hope you understood all about friction. Now when we apply these things into problems, that's when you should be. Let me give you a simple problem on friction right now before we go ahead. So let's say this is an object, is a mass of 10 kilograms sitting on a surface whose coefficient of static friction is 0.4 and the coefficient of kinetic friction is 0.3. And it's a horizontal surface. And the problem goes like this. The object just begins to slip. The object just begins to slip. When a certain force is applied. The object, you can write it down in words, don't just, the drawing alone is not enough. Okay, draw the diagram. It's a very important thing to draw the diagram because you need to draw forces on the diagram later on. So make a good enough diagram, not a tiny one. What did I say?
An object begins to slip.
Yeah, the object just begins to slip when an applied force, when a force is applied. Find the applied force and the acceleration of object after slipping. So So the answers come out like this. The applied force for it to just slip comes out how much? 39.2 newtons. And what happens after it slips is definitely an acceleration because the force is still 39.2 forward. So the force is still 39.2 forward, but the force backward is now not Fs but Fk. You need to evaluate that Fk now. What is Fk as it starts moving? Fk is going to be 0.3, this constant, times the normal reaction. So the weight is 98, therefore the normal reaction is 98. This one is how much? 29.4 backward. Now you can see that this 10 kilogram object is being acted on by two forces. One is 39.2 forward, and there is a force of opposition of 29.4 backward. Are they balanced forces? And so which law is going to come in now? Second law. The net force is equal to ma. So the net force is equal to ma comes in. Net force is this 39.2 minus 29.4 is equal to ma. And then find out the acceleration. So that will be 9.8 is equal to 10a. So acceleration is 0.98 meters per second squared. So once the object starts slipping, it will slip at that acceleration. Okay? Any questions on this?
Can you just read that up there for a second?
Okay. It's already 2 seconds.
So it's a little more.
We can take a picture if you want, and then fill it up later. So the concept is very clear here. First, understand what's a normal reaction, and then find out how much is the frictional force, and the frictional force comes out exactly 39.2. So that should be the applied force. The frictional force is 0.4 times 98, which is the applied force for it to just get it going. And once it starts moving, then the friction drops to a new value of 29.4, and so the net force is equal to ma, and you just work it out. Okay? Will? Now, let's look at connected objects. Connected objects. What happens when objects are connected to each other? Like, for example, if I have a pulley, and if I have two objects here, and this is a 5 kilogram object, and this is a 4 kilogram object. Now this is a connected system, right? Question is, what is the acceleration of the system? In other words, will this move? Will this move? With what acceleration? Okay? Assuming there's no friction on the pulley. So listen to me as to what you should do in this case. The first is a little bit of logic thinking. The logical thinking is this. What is going to happen? That you must decide. Now if you go wrong logically, there's nothing wrong with it. You will get ultimately wrong answers. Then you just understand that something's gone wrong, go back and fix it all. Okay? So there's no big danger of logically going wrong. All right. So logically, which way do you think this moves? So will it accelerate upward? Hopefully. If this is accelerating with an acceleration A, what do you think is this one doing? Now that is a logic kind of a conclusion that you take first. Now let's take one object at a time. Connected objects, you take one object at a time and apply Newton's second law. Take one object at a time. Don't take everything together. So look at this object for the time being, this one. How many forces are acting? So that's the next thing to do. You have to draw the force diagram. Draw the force diagram on this. What forces are acting on this? One is the weight, don't forget that. How much is the weight? 39.2 newtons. That is the weight of the object, downward. What else is acting on this? The tension. What do you know about the tension? Is it equal to 39.2? Yes, no? If tension is equal to 39.2, how can it accelerate? When will this force be equal to this? When it is at rest or moving at a? Now, is it moving at a constant velocity? So t is greater than 39.2, surely. Now let's look at this object for the time being. We already understood the physics there. So here, the force acting downward is how much? 49 newtons. What's the force acting upward?
Tension.
It is tension. Is this tension and this tension the same?
No.
It is, because it's the same string.
Oh.
As long as the string is the same, the tension is going to be the same everywhere. I think I discussed this earlier. Alright? As long as the string is the same, the tension is going to be the same. It's the same string, it's just that it's rolling over a pulley, and pulley is frictionless also. So these two tensions are exactly the same. Now once you write down this, let's apply Newton's second law for this object. Which one is bigger? This is bigger or this is bigger? Tension is bigger. So you write T minus 39.2 is equal to MA. Set up that equation. Now since there are two variables, don't worry about it. Come back here. Apply Newton's second law here. Which is bigger?
The 39.
The 49 is bigger than this because it's accelerating downward. So write 49 minus T is equal to 5A. See, I'm writing Newton's second law. Net force is equal to MA for each object. Take one object at a time. Take one object at a time. You applied Newton's second law to this. You applied Newton's second law to this. And now you have systems of equations. You can eliminate t very easily from here. Can you see that? Add the two equations. You'll get t and t cancelling off. So 49 minus 39.2 is what? 9.8, correct? Is equal to, add this up, 9a. So what is a? So 49 minus 39.2 is 9.8. 4 plus 5 is 9. How much is the acceleration? 1.09 meters per second squared. So when you release these two systems, when you release those two systems, this is going to come down with 1.09 meters per second squared, and this is going to go up with 1.909 meters per second. Now, using this number into any of those equations, we can find out the tension. How much is tension? How much is tension? Just apply. To find tension, 49 minus T is equal to 5A. Right? So A is 1.09. And then you can find out T will be equal to 49 minus whatever it is.
What's the acceleration on the last problem? On the top side?
Like 9A.
Mr. Sam.
What's